Okay, so let's start. Welcome everybody to this week's COVID math modeling seminar. Welcome to the seminar from wherever you're tuning in. I hope you're keeping safe and healthy. Today, we're delighted to have our speaker is Niayesh Afshordi from the Perimeter Institute, who will bring a cosmological perspective to this important problem. And he'll talk about local drivers of growth and containment for the pandemic. Niayesh.
Thank you very much, Kumar, for the introduction. Thanks, everybody, for tuning in. It's a pleasure to talk at the Fields Institute for the first time. Though we're not very far away geographically, but this will be my first time, albeit virtual. And well, welcome. Let's get started. Today I'm going to talk about our work on local drivers of growth and containment for COVID-19 pandemic. This is a work that we've recently done with over the past few months with Ben Holder from Grand Valley State University, who's been on sabbatical visiting us in Waterloo, as well as Matt Bahrami and Danny Litzblau from Wolfram Research Institute. Now, before I get into what we do, I just want to invite you to visit our COVID dashboard, where you could find cloud simulations for every US county, up-to-date resources, open data, and immunity maps. And our first paper on this topic, which you can find both on arXiv and medRxiv. In fact, my first submission to medRxiv. Hope you get to explore this. All of these resources basically at your convenience. And this is in fact an example of what you will find if you go to our dashboard. You could in fact use our model, based on our model, look at various counties in the United States and start your cloud simulations starting at some time with social mobility, which you think a county might be having, as well as the length of the simulation, use of face masks, and other properties. And then you get something that looks like this and more, which forecasts mortality based on the past data and our best fit model, as well as properties of that county, like population weighted density, population sparsity. These are the kind of things I'm going to talk about, but these are properties that we have first tabulated for United States counties. And Canada, of course, we will next. We live in Canada, but as it turns out, unfortunately, the data in the United States is much richer as things stand, and can be used much more effectively to understand the models of epidemic. But before we get there, let me tell you what I do for a living, just in a couple of minutes, just in case you find me somewhere else. I am, in fact, a cosmologist and astrophysicist by training. I work on physics of gravity most of the time. Just today, I'm going to play epidemiologist on TV, but under my day job, I usually do work on how Big Bang looks like, how quanta gravitates, how we can see the dark universe, and what lies at the bottom of a black hole. And these are some pictures you may find in my talks if you listen to me any other day. But then this happened. There was a pneumonia of unknown origin, as we all know, back in late December. Cases seemed clustered around a seafood market in Wuhan. That was close around 1st of January. There was the source was identified as a novel human coronavirus sequenced on 12th of January. The virus was later named SARS-CoV-2, and the disease named COVID-19, named after coronavirus disease. 19 is standing for the year. And it seems to be similar to the other bat coronaviruses that may pass through intermediaries to humans. Of course, we know that didn't stop there. On March 11th, COVID-19 was declared a pandemic. You can see the rise in daily confirmed mortality that basically picked up around March and then continued, peaked sometime around the end of April, and then appeared to have flattened more or less. And many countries have been affected, some very severely and some much less. by this outbreak, by this pandemic. So you see some countries like United Kingdom and Belgium had many deaths per million population. So this plot shows the deaths per million population versus daily confirmed deaths per million population. Other countries like United States and Canada haven't been quite as much affected, but things aren't quite settled now. There could be secondary outbreaks. And some countries are just getting started, and who knows how far down this phase diagram they're gonna go. Now, the questions that are in the minds of all of us who are witnessing these events unraveling, even from an astrophysicist's perspective, is what factors drive epidemic growth and decay? Can US county differences, the wealth of data that we have for the epidemic in the US, as well as all the other demographics, settlement, and weather, allow these factors to be identified? In fact, we are in a unique situation in terms of epidemics because of the wealth of information that we have regarding this epidemic and regarding everything else like human social mobility that's available, say, through cell phone information these days. However, if we could identify these correlations, that doesn't mean there is causation involved. As we know, correlation is not causation, and it's often the case that correlations between different variables is in fact caused by a yet third underlying cause. So to actually understand causation, we need a mechanistic or a causal model. And then the most sticky question of all is, has herd immunity been reached anywhere in the world? And then finally, the most important question for policy making, which affects all of us, is what are the best steps to manage or avoid future outbreaks in each community? In fact, let me tell you the first question that came to my mind when this thing started was that, do both these places have to go into lockdown when a pandemic hits? On the left, you have Kodiak Island in Alaska, and on the right, you have Manhattan Island in New York State. And you may anticipate what I'm gonna answer from the kind of question I'm asking, but this was really the question on my mind. The sincere question is that, what are really the best mitigation strategies depending on where you live and what resources you have? So basically with this introduction, this is the outline of what I'm gonna present over the next 40 minutes or so. I'm gonna talk about the data that we're gonna use. So this would be US mortality data as well as other demographics. I'm gonna talk about the linear models that could explain the data. And then I'm gonna talk about nonlinear mechanistic or causal models that could fit the data. And based on this, I'm gonna talk about our inference regarding herd immunity. And finally, I'm gonna end with the lessons that one might infer based on this analysis on how one can manage pandemics such as the one that we are going through right now. So let's get us started. So the data that we used were composed of static data sets, such as demographic data from US Census, as well as population-weighted population densities that I'm going to talk about more. We call them PWDs. This is from Global Human Survey population raster image provided by European Union, which has population density basically on 250-meter resolution scale across the globe. We then used also what we call population sparsity, something that I'm going to introduce to you in a minute. Furthermore, we used time series data sets, things that actually were variable with time. So these, of course, the most important ones were the daily mortality and case incidents due to COVID that were officially registered as COVID. And these are compiled by Johns Hopkins University as well as by New York Times. So we use both of their data. We use weather, including temperature and specific or absolute humidity, and human mobility in workplace, home, and transit that is provided by Google. So this is an example of the kind of map that we're dealing with. This is the Boston metropolitan area. So the colors show the population density on 250-meter resolution scale, and different geographical boundaries show different counties that we are modeling. So like 25 would be the Suffolk County, but then there are other ones. And as you see, the population becomes sparser as you go farther out into the suburbs. So the thing we want to understand is that how does this distribution of population affect the epidemic growth? So let me tell you what is it that we're going to work with. So for every county, we're going to define two measures of population distribution. So the first one is known as a population weighted density or lived density, which is a measure of how many people you would see around you. And is a much better measure of density of population because it in fact only cares about places where people live. So what you do is that you look at the average density of 250 meter squared parcels in your, or pixels in your county, but you weight them by the population in each parcel. So if you compare these two counties, for example, they have the same population weighted density or lived density because every 250 meter pixel parcel here has the same density of people. But then of course the density here, the average density here is much lower than the average density here because of all these empty spots. But then when we compute population weighted density, we just, we weight them to be zero because there are 0 people living here. So these two counties have the same population weighted density. And we think this is a much better tracker of how epidemic can grow because of course it tells you how many people you see around you. And these empty places, there could be deserts, there could be lakes, they don't really matter for the growth of the epidemic. However, there is also another measure of population that we defined for the first time here, and we called it population sparsity. So as an example, compare these two different counties. Again, they have the same population weighted densities because these parcels are the same number of parcels and the same density in each parcel. However, you notice there are all these empty spaces above and below this parcel of population. This one, there isn't. So if there is an epidemic going on in this parcel, they can actually transmit it to all these 3 parcels that are neighboring them. However, if something is happening in this parcel, they could only transmit it to these 2. So you could see that the disease or the epidemic can grow more easily on the left, at least hypothetically, than it would on the right. And you would think there must be a way to quantify that. So we define this as population sparsity, and basically what we look at is how population weighted density would scale with the parcel area. So if you look at bigger and bigger pixels or parcels, how does the population density, weighted density go down with the area of the parcel? And we call this gamma or population sparsity. For these 2 examples, this is gamma of 0. So this is a perfectly uniform distribution. It has basic population weighted density. It doesn't depend on the size of the pixel. But here, gamma is 1/3 for this particular example. And gammas, in fact, vary between 0 and 1 for various counties in the United States. So these are 2 measures of population distribution that could affect how an epidemic grows in a community. So the other kind of information that we use is the data provided by Google in terms of people mobility. So this is average mobility in workplaces and in retail places, the one that is plotted here, and in transit stations. And these are only relative numbers. So they're compared to January 2020. So you see that you are basically at 0, but then around the time that the epidemic hits, essentially all different places, they all go down in mobility, and that's basically because of all the simultaneous lockdowns that happen in various places. But of course, the exact nature of that and exact rapidity of that is different. For example, you see New York City went into a much deeper lockdown, understandably because of the epidemic was hitting it much harder, compared to say Los Angeles that only decreased 50%. Or Grand Rapids, which is, I guess, a similar lockdown. And then it lasted shorter because you see the rise in the mobility that was faster. So this data is available as a function of time, as a function of county. We also then looked at the case incidence rates. At this plot shows the case incidence rates. And then also there is weather, there is temperature and humidity as a function of time that you could see is gradually rising as weather was warming up during the winter at later times. So for our first analysis, we actually fitted the logistic curve to these growth rates to find how fast the exponential growth was at early times of the epidemic. And you can actually fit a logistic, and the early part of that logistic tells you the exponential growth rate. And you could see you get a number with an error for different places. And then we looked at different metro regions, basically the top 100 metro regions in terms of the population in the United States, and correlated it, did a linear regression to find what actually is most correlated with this linear growth rate. So we looked at a lot of properties, and it turns out that there are 6 of them, sorry, there are 5 of them, I should say, that appear to be significantly correlated, at least most significantly correlated with the growth of the epidemic. And these are 5 that actually make sense. So the biggest one is the mobility, as we discussed. When the lockdown happens, basically people stayed at home, and then the epidemic growth has stopped. So this is mobility 2 weeks prior, because you would think there's almost 2-week delay between detection of cases and the infection incidence itself. So that's more than 10 sigma significant. So this is very significant and is positive. But the second most important factor appears to be the population-weighted density that I introduced. More significantly, or more importantly, the log of the population-weighted density. And we're going to come back to why this log in fact matters. And that's at almost 5 sigma significance. So this basically means a tiny p-value of, say, 10 to the minus 5 or so. So, so that's also a very significant factor. The biggest population weighted density is, in fact, in New York City, in United States. And that had the biggest growth that you could see. Lambda is around 0.3 or 2.4 somewhere, the growth rate. And in fact, it was in our model, it was really driven by the population weighted density. That's in this model, if you think of it as an explanatory model, the reason New York City was hit so hard was because it had such a big population weighted density. But of course, we don't just look at New York City, we look at everywhere. This plot, in fact, compares the top 20 or so metropolitan areas, and the colors show that how big the correlation is, or how big is the contribution from these various factors are, from population weighted density, from population, from the mobility, and then other factors. So another factor that matters is specific humidity at around -4 sigma. So in fact, we find that the bigger the humidity, a specific humidity, the slower the epidemic grows. Population sparsity, as one may guess, also matters. The sparser the population, the slower is the growth of the epidemic. And the median age has a marginal effect. The older populations have a slowly faster growth of the cases in this case. So this is our first exercise, and it was just looking at the early epidemic. And we actually find these significant drivers. So the next thing we did is that we actually went beyond the early epidemic and look at the entire duration of the epidemic. So we can, in fact, fit for an exponential growth rate by looking at the daily mortality as a function of time. And basically what we do is we look at 14-day windows and then fit an exponential growth rate to that 14-day window. And you could do it for every county as a function of time. So we rely on mortality statistics for this exercise because it traces incidence growth rate, but it does have some delay. And most importantly, it is, even though the statistics, there are fewer mortalities than cases, it doesn't depend on testing rates and bottlenecks. So it's much less dependent on human policy decisions and the number of tests, the kind of things that is very hard to model and predict. There are fewer issues also with the reporting and methodology, even though we all know there are missing deaths. But our hope, and I think we have some evidence for that, that they don't affect this growth rate very significantly. We use a data set, basically using this methodology, we have more than 5,000 growth rate values over time and counties, different counties over 260 of them give us different values that we can actually fit the curve to. And then at different times, you could actually get different values. And again, we tried two different approaches. We tried the linear regression to identify the most significant drivers. And then what I'm going to tell you next is, that we're going to use a mechanistic or a causal model using a renewal equation or a version of renewal equation that is used in epidemiology to give a nonlinear model for the growth rate. So this is the linear analysis, and you don't have to pay too much attention to the numbers. Just going to walk you through this. So we did basically two analyses. One fitted to essentially everything we could get our hands on, which of course there could be more, but we tried a lot of different things here. And then a second exercise was just fit to the things that are significant, basically more than 3 sigma significant in terms of their TS statistics. Because the things that are not significant are not really that important, or we cannot establish that they're important at least given current data. For example, we established that the number of people per household, if you do a joint fit to all these quantities, doesn't seem to be a significant driver of the epidemic, even though it seems counterintuitive. But it appears that the number of people in household doesn't really matter very much if you account for these other factors. Moreover, if you look at various weather factors, it seems that a specific humidity 2 weeks prior to the mortality appears to be much more correlated than everything else. So basically, if you look at then the most significant drivers, we identified the same things that we found for the case growth for the metropolitan areas. So basically social mobility, the population weighted density, population sparsity, a specific humidity, and median age. And the numbers that we got are actually quite consistent, even though it's a very different type of measurements. This is for all times, the early growth for metropolitan areas was for the early times. We here at the county level, we're looking at the small and big counties. So there's very different type of analysis, and yet we get the same result. But since we do look at late times, we actually get 2 additional dependencies, which is interesting. We also find a very significant correlation with the death fraction, the COVID death fraction in that county, and that's at 10 sigma level. So basically, the larger the fraction of people, a fraction of population who die from COVID-19 in that county, the smaller is the epidemic growth rate. And this is a dynamical quantity because, of course, at later and later times, there's a larger and larger death fraction. And that appears to be negatively correlated with the growth rate, independently from social mobility. Social mobility is also very significantly correlated, as we had found before. But in addition to social mobility, there seems to be an independent correlation with the death fraction. And there is also an interesting correlation with the total annual deaths in that county. That I think, I'm not going to say much more about that, but I feel that has something to do with the coarse graining on the size of the county and might be related to what we call the normalization group in physics. But I'm not going to talk more about that here. But of course, these are correlations. That doesn't mean that it actually causes, any of these actually cause the epidemic to grow. You need the causal model to have a convincing description of what might be happening and what's actually driving the epidemic. I mean, what could be happening is that there could be some underlying cause that causes all of these, and that also drives epidemic. So just this correlation doesn't imply causation. So for that, we move on to a physical or mechanistic model of the epidemic. And to do this, we actually have to kind of reinvent some of what is done in epidemiology, but with a different flavor. And the flavor has to do with the fact that there is a lot of randomness associated with understanding of this disease. Some people stay sick for a long time. Some people don't show any symptoms. And it just seems that this disease appears to be very nonlinear. Now, it's not that other diseases are necessarily very predictable, but this nonlinearity or non-predictivity seems to be kind of much more pronounced for COVID-19. So in order to model this, we basically decided to model this as a random walk. And here, what I'm showing here is basically the x-axis or horizontal axis is the stages of the disease, which I denote by C. You could call it think about it as compartments or COVID. And this is kind of familiar in epidemiology as a compartmental model, except that this is a continuous direction now. It's not a discrete one. But also you can actually go back and forth between these different stages. So you could be exposed and infectious, become infectious and then become exposed again, so it won't be infectious. You could become hospitalized for a while and then cut back to become infectious. So basically the idea is that there is a random walk going on which describes the progress of the disease. And this is in contrast to standard compartmental models that the progress only goes one way. So here the idea is that you can go both ways. And the vertical axis, I have basically the density of the people who are exposed, or the people who are infected, if you will. And basically the distribution comes from the rate of injection. So people who are exposed, they start from here, and then they start a random walk in this space, a continuous random walk. Of course, early in the epidemic, there's a lot of people who are exposed. So this will be this red curve, fewer who are infected and hospitalized. Late in the epidemic, then basically there has been time. So people who were exposed, some of them have been infected. So there are more infected people and more hospitalized people compared to those who have been exposed. And we model this by a diffusion plus decay equation. So the idea is that basically over time, the distribution evolves. There is injection that's happening at C equal to 0. But then there is evolution according to this diffusion plus decay equation. So the idea is that people are doing this random walk in the space of the disease until they recover or they are removed from the infectious pool. They are quarantined effectively, so they cannot infect others, because that's the only thing that we're modeling is the spread of disease. Because individuals, people could be hospitalized, but those won't be, so we're not modeling that because they won't be contributing after they're hospitalized to the spread of the disease. So our model really just concerns mostly with the exposed and infectious phase, but really we're solving a continuous equation which has a diffusion part that has to do with the random walk and a decay part which has to do with the quarantine or recovery. And there's a time scale, which is, you could think of it as a diffusion time or the incubation period, which is related to how long it takes from exposure to get to becoming infectious, but it's a random process, so you cannot actually predict exactly how long it takes. For some people, it takes much shorter. For some people, it takes much longer, and some people will never actually become infectious. They just recover before that happens. So that's the first step, is how a disease progresses in an individual patient. But then the next step is what happens, how people can infect each other. And here's, I'm using my top of the line animation skills that I did in Keynote. So here, these are, you think about people as particles. The bigger ones are the ones have a bigger infections probability. They can infect more people for farther distance. The red are infectious, blue are exposed, and green is susceptible. So, so you can see, I press, so you see people move, and you should pay attention. If you didn't pay attention, let me, this green guy is susceptible now, and it just passes through the red guy, and it becomes blue, it becomes exposed. So you see, this is how infection happens. It's very top of the line graphics here. But the physical thing that I'm trying to kind of demonstrate with this cartoon is that basically you have an incidence rate for infections, which is basically new infections per time per area, which is the product of the susceptible density times infected density, or basically density of these two populations, times the infection rate, which in physics we basically call this collision rate, or the product of the cross section and the relative velocity. So the bigger these guys, the more people they can infect around them, which has to do, now exactly what this means, it probably depends on the variety of factors. Like if people are social distancing, these are probably a smaller, the infection rate is a smaller. If people using face masks, this would be a smaller. So the cross section is not actually geometric cross section, but it really has to do with how likely you are to get infected if you pass by, or get exposed, I should say, if you pass by another person who's infected. And we assume that early in the disease, when you just are exposed, you don't have time to incubate viruses in your body. So this beta is 0. So the people who were here, you just expose. Before you get here, you basically cannot infect others. But when you get to this infectious compartment, then you can expose others. So beta, which is essentially your cross-section, we assume it is 0 when C is less than 1, and it's a constant beta bar when C is bigger than 1. Of course, this constant could depend on other properties of the county, or and that's what or can depend on time, but we assume it doesn't depend on C anymore, just for simplicity. And if you're interested, and you can ask me later, I can show you the more mathematical formulation of this in terms of renewal equation that's more familiar in epidemiology, in mathematical epidemiology. So this description, if you bear with me this long, it gives you a result. It basically tells you how exponential growth rate depends on these various factors that I introduced. So lambda is basically some function which is known as a Lambert W function, which is basically just inverse of an exponential times a linear function. But it has a name, it's known as a Lambert W function. So it turns out that the real formula in this physical model or causal model of epidemic is not linear in terms of these parameters, but rather has this nonlinear form. So it depends on beta bar, basically this infection rate or cross section as I introduced. Depends on S bar, which is the density of susceptibles. Depends on diffusion time or incubation time as introduced before in this random walk process. And of course, it depends on the exit rate, which is the rate at which people get quarantined or recover from the disease. Now, in case you don't remember this Lambert W function from your applied math courses, it's a function that looks like log of x for x being very big, and it looks like x for x being very small. And you notice now, this is the log of population weighted density we were talking about. Of course, there is a square here, which we didn't have. But this is where the log of the density comes in. This W function early in epidemic, where this is big, when you have fast growth, actually goes as log of everything. At late times, it's linear. But what happens at late times is this goes to 0, and then basically lambda becomes negative because this D is positive. So let's see how it actually fits the data. It turns out that it fits pretty darn well, which is bizarre. But in fact, this simple model, which has 9 parameters, in fact, the same number of parameters as a linear model, can fit all the data from the counties, all the 5,000 data points that I showed you, pretty well. In particular, I mean, the measure that we often use as a way of goodness of fit, as a measure of goodness of fit, is reduced chi-squared, which is basically the variance of, or the difference between the model prediction for this growth rate. So this would be these red curves, is the best fit model for every county as a function of time. And the blue is the actual measurement for the growth rate in that county. So the difference between these two divided by the error, which is this blue region, S squared, average over all the data in all the counties is just 1.3. If you had the perfect model, this would be 1. So we only a little bit higher than what statistical errors allow us to be. So the model is not perfect, but it's pretty darn good. And basically, it just means that our effective errors are 15% bigger than the measurement errors. Another surprising thing is that there is basically universal and very accurately measured decay rate for the disease. Essentially, all these places that the epidemic stops, either because of the lockdown or because of herd immunity, as I'm going to discuss, the epidemic decays with a universal value of decay constant, which is basically 1/18 days roughly. And it's consistent across all the counties across the states. And all the data we fit basically this is the minimum decay rate that you get, which is basically 1/18 days. And you can see it's here, basically this plateau that you see in all of these, this kind of reach 1/18 days. Now, some of them, they don't decay as quite as fast, and that might be that because they're not quite as their minimum. And in fact, some places are growing, like LA. In fact, the epidemic is growing now. But the minimum that you get is this value, which is pretty universal. So there are 9 parameters that we fit for. There is a dependence on age, which basically there is a best fit value, and then for this diffusion parameter or incubation time period, which depends on age. We model it as a power law, so that power is measured to be some negative value. So that means that the older you are, or the older the community is, the faster the incubation happens. There is this exit or decay rate. There are these parameters that quantify beta, so dependence on social mobility. So the infection rate depends on social mobility, depends on humidity, depends on sparsity, depends on the total death in the community. And the most interestingly is what I mentioned before, is that there is also this CD parameter, the dependence on the total death fraction in the communities. That means, in fact, what we find is that a very good model that fits all this data, in fact, it leads to all these red curves that you see, is that the susceptible population decays with time, or in fact, is proportional to the population weighted density, which I discussed before. But then as time progresses, it exponentially decays, like with the constant time, the total death fraction in the community. So the more people die in the community, the fewer are the people who are susceptible. And that's basically what comes out of our feeds. So this is another example of the kind of fit that we have. So this is, so in fact, I advertised our dashboard early on that you can go to. And you could see basically how well model would predict things. So model only has nine free parameters. And the data, you could look at every US county or at any time you want. And you see that you could pick some time and see basically how the model would predict the disease would grow, or the mortality would grow in that county, depending on where the county is at that point, and basically the properties of that county, like population weighted density, sparsity, humidity, social mobility. Of course, social mobility is available at some time. Beyond that, you have to specify what people decide to do with the social mobility. For some of them, it worked well. For some of them, it doesn't work very well, but that's kind of the nature of the models, that there are statistical fluctuations. For example, this is Boston. You see that there are places, there are spikes that are not caught by the model. Some of these could be due to reporting inconsistencies. That happens a lot. In fact, as it turns out, just counties decide to dump data on one day for a random reason. And that makes our jobs very hard, but nevertheless, we have to deal with them, and they all go into the errors. So, we see that the model seems to be predictive and seems to be doing well for different places. Some places like Suffolk County in Boston, the epidemic had a big peak, but it's decaying. Others, it seems to be still ongoing, like LA or Miami. So now let's get to the most sticky topic. And can I ask you, Komar, how much time I have?
Yes, you have about 20 minutes.
20 minutes. Okay, thank you. So hopefully that's plenty of time. So now, what about herd immunity? I mean, of course, this is one of those things that, I mean, of course, I haven't been doing any epidemiology until 3 months ago. But I kind of learned that this is possibly the most kind of loaded word that you could use, at least when talking about this pandemic, and of course for good reasons, because you don't really know what's happening, and this is such a big mystery. So let's talk about what it actually is and why people always talk about it so much. So there's so-called concept of classical herd immunity, which is if a large enough fraction of population achieve immunity, either through infection or through vaccines, then the production number, and this immunity lasts, or at least as long as it lasts, then the production number of the epidemic or the disease falls below 1. So this, the infamous R which was a large number early in the epidemic for COVID or any early outbreak, falls below 1. And when that happens, basically that means that an infected person cannot find enough susceptibles around him or her to infect them. And basically the disease would die because they cannot actually be transmitted to others. So at that point that where R falls below 1, in our language, the exponential growth rate becomes negative. And then the disease should decay, right? So that means that you don't actually have to vaccinate everyone in a county, or not everyone needs to be immune. There should be enough people who are immune so that the disease cannot spread. Right? However, you should be aware of the overshoots because, and this is something I'm going to show. Sorry. Because just because you reach herd immunity doesn't mean that the disease stops growing. It just means that the R falls below 1. There still can be a spread of the disease, especially if there are a lot of people who are infected. So typically, especially if you don't if there are no interventions, you would overshoot the herd immunity threshold. And I'm going to show you some examples of this. So estimates for COVID-19 herd immunity threshold has a large range. It actually ranges from less than 20% to 70%. And there are a few papers that actually advocate for these lower values. And this has to do with basically the heterogeneity of the population. So the people who are, some people are more efficient in infecting and others are less efficient in infecting. And this heterogeneity, so if you assume a completely homogeneous population, the early estimates suggest something like 70% to reach herd immunity. But then there's more recent literature that has looked into this, and they suggest that it might be a smaller number depending on how heterogeneous you think the infection is in a society. There are, of course, big questions that I have no expertise to address. For example, how accurately you can test immunity. So there is T-cell immunity versus antibody. And one may be permanent, the other may not. And these are all kind of open questions regarding this, this pandemic. So what we do instead, and it's again something that's I think probably novel because now we have so much data that we could actually model this given the human mobility and also some other data that's now available for human population, is that in fact you can look at correlation of COVID death fraction with the growth rate of epidemic and with all the other driving factors because they are all important. You cannot just look at one thing, because that one thing, its correlation might be confounded with other drivers, which are all significant. But if you actually manage to pinpoint all the significant drivers or the physical drivers on an epidemic, then you could in fact identify or isolate the dependence on death fraction, which would be related to the immunity. Because of course, the more people are infected, the more people would die. It's a tiny fraction, between 1% to 3% of the infected. So that's the big question, exactly what number. But that is, in fact, a tracer of the people who get infected and potentially reach immunity, although how long immunity lasts is yet another question that needs to be addressed. So in fact, this is what you get from our model. So we actually fit all the data, as I said, all the 5,000 data points, and with these 9 parameters. And one of those parameters is dependent on the death fraction. And on the left, you could look at some average US county. If you just take some properties of an average US county, it's a county with, say, population about 1 million people, with a population density, which I don't have exactly off the top of my head, but I guess if you could go back here, there is we have a table in our paper with the average population weighted density, which is, I guess it's exponential of 8.24. I don't have the exact number with me right now. But it's some number around a few thousand. Sorry, I have to go a bit. It's some number around a few thousand. And you could look at how much the exponential growth rate of the epidemic depends on the death fraction. And of course, early on is positive for a typical US county. But then the more people, as more people die or get infected, and of course, some of them would die, then this growth rate slows down. And what we find based on the best fit model is somewhere around the death fraction of 1,200 plus or minus 100 per million population, this becomes negative. Now, this is a little bit confusing, this data point. So every data point here is in fact fitted to all the US counties, but during the times that the death fraction was during this time, and if you go to a larger death fraction, the number of counties that ever reach that number, that death fraction becomes smaller and smaller. So, so there are fewer counties that contribute to this data point than it does to this data point, for example. But nevertheless, basically all the counties contribute to these data points, but there are independent fits for these different compartments of death fraction, basically. And the lines are actually this global fit that uses a nonlinear model and should fit everything. And we see that this basic model that we have for herd immunity, which is this exponential dependence on the death fraction, captures reasonably well the dependence, basically how the growth rate depends on the death fraction. Now, of course, individual US counties had interventions. Most of the US counties had some version of lockdown. And here I show that if there's average US county had 33% reduction in social mobility, which is in fact less than most counties. Most counties had a more severe lockdown, or like 50%. But even for 33% lockdown, you would see that everything is smaller and you reach this level of basically zero growth earlier. But of course, that doesn't mean that's the end of the epidemic. And what you can see here is a phase diagram that shows basically the flow of, this is something that you could, in our equation, you could show that for every total death fraction, for a given social mobility, you could predict, at least statistically, the daily death fraction. And it's basically like a phase diagram that we have in physics. So this is the time derivative of this axis. And the herd immunity is the fixed point. Basically, that means that if you're sitting at this point and there's no lockdown or anything, the epidemic doesn't grow because there are enough people who are being infected in that community, according to our best fit model, that the epidemic cannot grow. Of course, if you're somewhere up here, and in fact, if you say have no intervention, those would be red curves, you would overshoot the herd immunity. You would try to go up, reach a peak at the herd immunity, but in fact, the epidemic does continue and the more people will die. And that's known as an overshoot. So on the left, you have the typical US county. On the right, I'm showing New York City. And in fact, you see the data from New York City, and the green circle or green disk is the herd immunity threshold based on our model, which is in fact larger for a than compared to a typical county. A typical county is somewhere around 1,200. And for New York City, it's closer to 1,700 is the herd immunity threshold. And of course, New York City has overshot it. And that does happen if you have late or insufficient intervention. So you actually go up, and even though there have been interventions, you didn't go all the way up. That could have been much more devastating. That was still enough for you to overshoot the herd immunity threshold. Now, the 33% for a typical US county is in fact enough for you to end up at the herd immunity threshold, at least according to our best fit model right now. And that means that if you raise the lockdown at this point, then the epidemic shouldn't grow, at least if the model is correct. So these are examples for different US counties. You have basically 4 counties in 4 corners of the country. You have LA and Washington state. So this is Seattle. And you see they are far, far from herd immunity, according to this model. Boston is just heading for it. It might be just around it, although it's basically close to it. And when you're close to herd immunity, it turns out every little thing matters. So like the change in weather could actually take you below or above it. And this is Miami, which is, I guess, southeast of the US, and that's also far from herd immunity. And basically what this means that these ones that are far from herd immunity, as soon as you raise the lockdowns, then they're gonna go back up into go back up. And if there is no further lockdown, they're gonna overshoot the herd immunity threshold. Boston, however, appears that it's close. So there's, I guess the prediction of the model is that there won't be at least a significant second wave for Boston. So you can actually go and make a map of where this you think might have happened. And actually something you can already notice here that this point is in different places for different counties. For Boston, it's somewhere around 1600. For New York City, it was about 17 or 1800 per million population. For LA, it's closer to 1100. So in fact, this does depend on the properties of the county, how humid it is, what is the population weighted density most significantly. So you actually need to know all of that to know exactly where what their herd immunity threshold is. And according to our best fit model, as of July 7th, these are the places that had reached or are close to herd immunity, assuming that it's a permanent phenomenon. If it is, so it's basically the places that are around Northeast, going from New Jersey all the way to Boston or to Massachusetts. And then there is the area around Georgia and Louisiana that basically some counties have had severe outbreaks. Now, another interesting thing you notice is Navajo Nation, even though there are very few deaths there, it's a significant enough fraction of the population, and they have a small enough population weighted density that this model, if you trust it there, it predicts that they're also close to the herd immunity threshold. However, this is only less than 10% of the US population. So more than 90% or about 90% of US population, which is vast majority of the counties, they remain susceptible, and they have to, if they don't have any measure of social distancing, lockdown, or face masks, or some combination of those, then there will be a second wave or there will be outbreaks, as we are seeing happening in the southern United States. So the few hard hit areas that, I mean, examples are New York City, Detroit, New Orleans, and these are places where mortality is somewhere between 0.1% to 0.3%. They appear to have passed this threshold, and here you could see a histogram of those places. So again, this is a logarithmic axis. So a small fraction of the counties, of order of 100 out of 3,000 counties. Which of course they happen to be most populated counties, because those are places where the population density are big, and these were also the ones that have been hit hard early on. So that's kind of our prediction. And in fact, for every prediction, it's only as good as it can be tested. And this is kind of the hard test for a model. So this case study is New Orleans, I guess I'm not sure how to pronounce it. So some counties, as you saw in the map here in this southern US, have reached herd immunity. It's a small fraction of them, but still some of them are. And then the light blue or cyan ones are close to it, but they're not there yet, basically, or they're within 1 sigma confidence. So they have reached herd immunity. What if a county reaches herd immunity according to our model, but its neighbors have not? Now, cases across the US South have been rising steadily, as you all know. And basically, most of the population in these regions remain overwhelmingly susceptible, with a few exceptions that I mentioned up here. So the question is, will the outbreak spill over to counties that have reached herd immunity? And this is an example of cases in Orleans Parish, where New Orleans is. And then death, you see the death has been going down, although it might be plateauing. The cases have been rising. If you use our dashboard to do a prediction, say starting from early May, you see that, so we do predict this, basically decline due to herd immunity. That's, as I mentioned, has been reached there. But then there are these places where you see at late times there are deviations, and this is kind of 1 or 2 people who die of COVID every day in this Orleans County. It's a small number, and it could be a small number of statistics, but the question is basically, does this mean that herd immunity is in fact not reached, or does it mean something else? So the prediction, and this is the prediction of basically this hypothesis of herd immunity based on our data, is that mortality will plateau in New Orleans or other places that are at herd immunity, but are surrounded by pools of infection. The prediction is that it reaches lambda equal to 0, so it would plateau, but there shouldn't be any community outbreak because the community itself is not susceptible anymore. Of course, people could keep bringing it in from the neighboring counties, and that's going to give rise to a plateau here, but they shouldn't get exponential growth as you would get from a community spread. The cases can rise due to increased testing, and in fact, testing has been steadily increasing in the United States. So this rise can be completely attributed to the number of tests in New Orleans that increased by a factor of 3. Now, of course, the alternative, if they see that the mortality starts rising and then you see a second wave, is that immunity doesn't last. So whatever we found worked around its first peak, but then it doesn't last for more than a couple of months maybe. And then you could have a second wave. And the data as of now is not exactly conclusive on this, at least the data that we have, because the duration of US epidemic has been 3 months. So the real test where rubber meets the road is whether you could, you have reached herd immunity, whether you can get second waves in these places. So I actually noticed I am kind of running out of time. So in fact, one way to understand this exponential decay has to do with the heterogeneity of the population, that super spreaders are in fact, as we understand now, are the primary drivers of the epidemic. And in fact, we can measure the ratio of the infection rate of super spreaders to vulnerables. And I think our explanation of why these places reached herd immunity, according to our observation, is that in fact, super spreaders are something between 30 to 100 times more likely to get infected than the vulnerable community who may die. And they reach herd immunity much, much faster than the rest of the population, basically. So, okay, so to wrap up, let me just leave you with some final thoughts. We did some, actually, another thing that comes out of our work is fits to incubation period and generation interval. And it's kind of surprising, but I don't have too much time to talk about it. It seems that there's less than 10% of exposed will ever become infectious, which is a very small number, and it does depend on the age of the community. But also it seems that our generation intervals are 10 times longer than clinical estimates of 3 to 7 days. So this is kind of, this might be an explanation for the so-called COVID long haulers, although we don't have any reliable statistics to actually fit this. Okay, so some final thoughts. So a physical approach to epidemiology, we think is more realistic than a simple compartmental model that has been widely used even today to model COVID, but it's more identifiable and tractable than more complicated social networks that is really hard to track. So we are kind of a middle ground between these two. So we think the community-specific intervention depends on population distribution, demographics, and climate of that community. So the question I posed to you, Kodiak Island in Alaska doesn't need the lockdown according to our model for COVID, but Manhattan does. So in fact, this is one of the few places in the US that doesn't need the lockdown. Herd immunity happens through depletion of susceptibles to super spreaders. It's not everybody that matters for this, it's just the super spreaders according to our best fits. The question is, can they be somehow identified through demography or biology? Counties are not islands, so this could actually impact our definition of herd immunity. And there are interesting implications for long haulers because we see much longer, basically generation intervals, but much more heterogeneity. Most people never actually get infectious. So, and I mean, the very last slide, so these are the things that keep me up at night, that evidence for immunity is decisive in my opinion, but does it last? What are the best ways to track social distancing or PPE use? That's very important for our kind of analysis. So, but maybe most important of all is how to balance the harms due to COVID against the adverse effects of lockdowns on mental health, economies, education, etc. So we think we have tools that can be used in order to do this kind of policy analysis now. And finally, scientists like me, and remember, I'm not an epidemiologist. I don't know what I'm talking about. I'm an astrophysicist. but we all have responsibilities to our societies. And then should we roll up our sleeves when millions of lives are at stake, or just stay out and leave it to the experts to handle the situation? Okay, thank you very much.
Thank you, Niayesh. Very interesting talk. A lot of interesting ideas there. We are short of time, but I think we should have a few questions. I'll let John Hong, who's online now, conduct the question and answer. John Hong, with your permission, may I ask the first question?
Yeah, of course. Yes, please. Yeah.
So one thing that I didn't see, or maybe you had and I missed it, is what happens about what's happening in between counties? Like, so you have something going on, a phenomena inside the county, but then it's not an isolated entity. Unfortunately, that could be rather important. How would you incorporate that?
That's an absolutely important point. And this is in fact what I was talking about here, is the counties are not islands. I think the amazing thing is that we managed to fit the data so well, given just individual county information, but there's obviously things that are missing. But those things are things that we have a harder time modeling. And I think those are things that kind of the next step of this analysis. So I think my kind of first order answer to this is that there are community spreads that are happening just because of the political boundaries of the counties that happen to kind of surround population centers. And those population centers is where community spread happens. So those are kind of contained to individual counties. But of course, the spread does happen from county to county, as I was arguing. But for that, you need kind of a more complicated modeling. And I think that will be important at some point. But I don't think that's the main driving factor. At least we don't see it in our fits.
John Hong will continue. Yes, some people who want to ask.
Right. Yeah, anyone would like to ask a question can raise your hand or send your questions to.
I have a question.
Yes, please.
Thank you. I'm Kenza Faska from Morocco. I'm assistant professor in International University of Rabat. Thank you for your presentation. It's very interesting. I have a question about, for example, from Morocco. Morocco decided to reduce the social mobility after the declaration of the six cases infected with COVID.
Yes.
And the number of deaths in Morocco is very reduced about another country. Have you studied the case of African city, for example, Morocco?
Well, unfortunately, that's kind of the next step of this analysis, to go into other counties or other countries, I should say, and other regions. The advantage of the US was that we have so much data that was available to us in terms of and human interactions, as well as COVID. So we had a little bit of control on what's happening there. And in other places, the data was just a bit harder to come by, but that's definitely on our next step. I feel the general lessons that we have here can be applied elsewhere, but the specifics, like, for example, the fraction of the people who are super spreaders, for example. So these are the kind of things that might be a specific to countries, and that needs to be modeled independently, but we haven't got around to basically do that yet.
Okay. In your model, what is the parameter that dominant in the difference about evolution in your model?
So there are several parameters, but as I discussed, there are basically three main driving factors. There is the population weighted density, how dense people are living together. There is the social mobility, basically how severe the lockdown is. And the third parameter is the herd immunity, which is basically the fraction of people who are infected in the community. So these are the three most important factors that kind of drive the epidemic. There are secondary factors that we discussed, but these are the three main important factors.
Thank you. Thank you for your answer.
Thanks.
Thank you. We have one raised hand and one question from the chat from Saga Kuma. Saga, do you want to raise the question directly? If you can unmute.
Am I audible?
Yes, yeah, please.
Yeah, so if we use the death fraction as the objective probe, and given that the hospitals now these days are following a good difference in the treatment protocol, means if we look at the protocol that hospitals are following these days, it's different. So
Yes.
whatever work you have done can be divided into 2 time spans where the treatment protocol changed and then compare the chi-square values.
Yeah, that's an excellent question and something we are kind of tackling with. The problem is indeed there is time dependence, but also there is geographical dependence. So I think the main thing that we need is some good measure of when the policies change, some continuous measure, and we need that across geography in different places. If we do have that, then we should be able to basically infer this. But yeah, so if, to add any extra uncertainty or dependence, we need to have a probe of it across the nation or across the globe if you want to do this globally. And some of these are available, but this one, in terms of change of policy, the thing is that changes of policy never happen instantly. They always happen gradually, and they don't happen uniformly either. So, so this is the kind of data that it would be great if it becomes publicly available, and if it is available, I'm not aware of it. But basically, exactly how the policy changes in a quantitative way across US or across the world, that's the kind of thing that we need to introduce into our modeling.
Thank you.
Thank you.
Okay, so I have Matthew, Professor Effendi on the line.
Yes, the following question, could you go to the slide where the continuous random walk?
Yes, let me continuous random walk. This is the one, yeah.
Yes. So now this could be physical and mathematical questions. I would like to compare 2 cases, the heterogeneous system with diffusion and heterogeneous system without diffusion.
Right.
The question is, can we say that total population size will be higher or will be exceed in the case of heterogeneous system with diffusion?
No, that's an excellent question. And to be honest, this slide itself doesn't say too much about the heterogeneity, because all we're modeling here is really the generation interval of the disease. It just tells you that if someone gets exposed, with what probability that person would be infectious at some later time. And basically what you do is you just saw solution of this equation gives you how likely it is for someone to infect another person at a later time. Now, whether these are just a small fraction of people who are doing it and they are much more likely to do it, or just everybody does it the same way, that doesn't come from this slide. Where it does come from is when we model the herd immunity threshold. And in fact, let me just show this to you because I have one backup slide on this.
Yeah, so very good. Mm-hmm.
Yeah, so basically what's happening is that you have the number of susceptibles that is decreasing as they get infected. Basically, you remove them from susceptible population through the infections. So this I star are the infectors, the people who are doing the infecting. But then there are different, this beta is not a universal factor. So beta is basically how the rate of getting infected, and people who kind of live in their house in an isolated way would have a much smaller beta compared to the people who just go around and interact with everyone, right? So basically what then we find is that the depletion of susceptibles then would be different for different populations. And in fact, if you just follow this simple equation, it would go as exponential of minus beta times some factor, some number. So the ratio of the susceptibles now to original number goes as a power law of this ratio of the mobilities or this infection rates. So basically what we can say by looking at this equation and basically plugging in this in our formalism, that basically there are 2 different populations. There are the super spreader population, where basically they are the same as the infectors. So they basically the I is coming out of S. Mm-hmm. But then there are also the people who are dying, the vulnerable population, but they don't have the same mobility. as the super spreaders. And basically, by combining this, basically we have a fit for, we can fit basically for this number, basically the ratio of the infection rate or mobility. And so this is where it comes in, is in modeling herd immunity, where the heterogeneity of mobility comes in.
Thank you. Well, we have last question from Abdul Qadir Hussein. I think you have questions the same related to the diffusion question. So if you can.
Hi, Niayesh, how are you?
Thanks, thank you.
So I was wondering, you know, where do you have the stochastic part in this diffusion equation, or is there a none? And the second question related to that is because you call this causal model, because in statistics we label causal different things, you know, like when we post stratify a population so that we can extract, you know, variables related to treatment and then identify the average treatment effect and then call that a causal parameter, causality. So like, how does that relate to this causality?
Right, good question. So the first one is that, so every individual patient is undergoing a random walk in this space. But if you look at the population of patients, then you could show basically using just a random walk theory, basically, that you obey a diffusion equation. So the diffusion is in fact a probabilistic description of the random walk. So it is a description of the stochastic process. Now the causal, what I meant was, I guess, not in the medical sense, but rather, or a statistical sense possibly, because I'm not familiar with that terminology. What I meant is that in a physical kind of terminology, in a sense that if you have a physical process that you understand the ingredients of it, then you can set the initial conditions and then predict what's going to happen. And this is like what we know we do when they say predict the positions of the planets in the sky or the stars in the sky. So that's the kind of causality that I have in mind. And in this case, this is a collision process for people who are interacting with each other and getting infected. So that's causal in this sense, in the sense that if you know the initial condition, at least you can predict the probability of what's going to come out of this.
Thank you.
Thank you.
Thank you very much. And I think we are a little bit over the time. So Kumar, do you think we should close here? And
yeah, let's wrap it up.
Thank you for joining, and thank you again for the speaker. And
thank you very much for having me. It was a pleasure. Hopefully I see you around sometime soon.
Yes, we should have you back.
Yeah.
Right. Bye.
Thank you.
Thank you, everybody. See you next week.